Well, we all know that the volume of a prism is the area of a base times its height. Now, if you got something like this nonagon, well, golly, that's some trig in order to calculate that. But we'll do that in the exercise, sample exercises. Instead, I'm going to take this prism and I'm going to chop it up into little pieces. I've got a center point up here, which is on this top base. It's in the center. And I'm going to draw this. And what I'm doing, you can see I'm carving out a pyramid. I can see a pyramid now inside the prism. And that pyramid has a volume exactly 1/3 that of the prism. Amazing relationship. So, well, just like the cone to the cylinder, so the volume is 1/3 the area of the base times the height. Well, before we solve this one, let's first understand the drawing. We have a static drawing on the left, but we can move this one around. We can see that we have a triangular base, and that makes this a triangular pyramid, A3, 4, 5 as a matter of fact. Well, since the triangle in the base is a right triangle, 3 times 4 is 12, half of that is 6. Since the area of a triangle is 1/2 base times height, that has a surface area of 6 square inches. And if I look at it this way, then the entire figure, the pyramid that is, has a height of 3 inches. So I'm going to take the area of that base and I'm going to multiply times the height. It's going to look like this. 1/3 the area of the base times the height gives me, of course, the volume of a pyramid. And there you go. 3's divide out nicely. I've got 6 cubic inches. Remember, the base here, that's where we got down there. That's where we got our 6 from. And we're good to go. All right, let's get the volume of this pyramid, hexagonal pyramid. We see we have a hexagon, regular hexagon for a base with sides of 12 feet. And this figure has a height of 17 feet. And on the left, you can see we're getting ready to work with the hexagon itself. Just a side note I want to mention here is, in case you were curious, you know, as long as its height is 17, as long as its height is 17, it doesn't really matter whether this pyramid looks like this or like this. It's still going to have the same volume. Just thought you might be interested to know that. This pyramid, same volume. Now let's get to solving. All right, we've got the hexagon. Gosh, we're used to seeing this by now. Sides of 12. We know that the sides are equal to the radius in the case of a regular hexagon. And we know that ubiquitous 30, 60, 90 triangle resides right here. Apothem radius. That's the 30, 60, 90 triangle. We've been doing this since last chapter. So the ratio of the sides, 1, 2, radical 3. That's not new either. We already know this side is 12. This must be 1. After all, it's also half of a side. So I can replace those ratios with 6, the 12. But what I really need is the 6 radical 3 for the apothem. That's the only thing we really need. After all, we know that when I am finding the area of a regular hexagon, it is 1/2 AP. And since I know that the pyramid is 1/3 capital B, or base times height, I'm going to substitute 1/2 AP for base. So now, let's just put some numbers in there. Well, 1/3 times 1/2 is 1/6. The apothem is 6 radical 3. The perimeter is 72 because after all I've got 6 12s. And the height of the figure is 17 feet. And since they were all feet all around, I know I'm multiplying feet by feet by feet, I have cubic feet. And I could simplify that, you see, conveniently by leaving in this form, you know, those 6's divide out nicely. So I can just take 72 times 17. I can do that pretty quickly. 72 times 17, so it's going to be 1,224 times radical 3. Pull out your calculator and use that radical button, and you should get 2,120 and 3/100ths. And that would be in cubic feet. All right, we're solving for x in this equation, and that would be the altitude of this square pyramid with sides of 10. Volume is given at 200 cubic centimeters. We know the equation. Simple substitution. Then we'll just put the numbers down, but we'll talk about units in a little bit. See, what do we got here? Well, easiest thing to do. Multiply both sides of the equation by, you guess it, 3. So now I've got 600 is equal to 100h. That's pretty straightforward, and I guess all we're going to do is divide by 100. But let's consider the units for a minute. These are cubic on the left, cubic centimeters, and we're dividing by square, and that does give me centimeters. So that makes sense all around. Height, 6 centimeters. Well done. Let's do another one solving for the variable, in this case height. Wish they would just used h. But we're solving for this height, unknown. We know the volume of this pyramid. And this pyramid has a triangular base, actually an equilateral triangle. You'll have to visualize that one. I'm taking a break from the 3D. And this triangle has sides of 2 radical 3 feet. Oh, so you know we're doing something funny with this radical 3. Let's first find the area of this base down here. And I'm going to rely on this formula. This formula is the area for a, well, the area for a equilateral triangle only. S squared over 4 radical 3. It's very useful here when we substitute in here. That's what we get. And remember, you've got to square the 2 radical 3. That's 2 squared times radical 3 squared. So that would be 12 over 4 radical 3. To last time I checked, 12 over 4 is 3. So all this just to get the area of the base. So the area of the base is 3 radical 3 square feet. And we're going to apply that to this pyramid. Okay, let's do another substitution. Now, the 7 radical 3 is the given volume. 1/3 times the base, 3 radical 3, times the unknown, the x. And you can see right here that this is going to be pretty convenient because I'm going to get these 3's to divide out very nicely. And that's going to leave me with, I guess, just radical 3x in the numerator. And as you can see, I've got a radical 3 on both sides of the equation. Just divide those out. And x is going to be 7 feet. Excellent. And let's just to check our dimensions again. On the left side, on the 7 radical 3, we had cubic feet. And these were, of course, square feet. When we divide cubics by squares, we're going to get linear or just plain feet. So it checks out okay. 7 feet is the height. And this is an interesting composite solid that we have here. We're going to take a cube, a 10 by 10 by 10 inch cube, and we're going to take away from it, we're going to extract from it a pyramid with a square base formed at the midpoints of this upper surface. And this pyramid also has a height of 10. So this ought to be kind of fun. And let's just get right to it. We've got the static drawings now, and we've got a drawing of the top view. So let's set up the problem. I know that the solid is, this overall solid is the cube minus the pyramid. I know the formulae. Well, the cube, let's go side cubed, and a pyramid is 1/3 the area of the base times the height. Let's figure out the base. Now, you're looking at these 45, 45, 90s. And since these are midpoints, I know you got 5, 5, 5 radical 2. And sure enough, you got to square it. And when you square it, I'm just expanding in case you've forgotten. Remember, you're squaring the 5 and you're squaring the radical 2. 5 radical 2 squared is 50. So that would be 50 square inches. And all the smarty pants out there, you said, Mr. Bannish, wasting your time because this is 10 inches, this is 10 inches. That's a square of 100 square inches. And this figure is known as a midpoint polygon, or midpoint quadrilaterals more specifically. And it has an area exactly 1/2 of the original polygon. Half of 100 is 50. So if you are that smarty pants, thank you for paying attention in chapter 8. But no matter how you got it, that area is 50 and you need that. Because now we can carry on here and finish it off. Substitute. We've got 10 cubed minus 1/3. Area of the base is 50. The height of the, whatever that thing is, the height of that pyramid is 10. So let's do some arithmetic. And I'm doing this in my head. 500, 1/3 of 500, 166 and 2/3. And when we subtract, they wanted decimal, so we will go decimal there. And you're going to end up with 833 and 33 hundredths cubic inches. And that one's done.